Okay, welcome back everyone to the second week of our Game AI workshop. So this week we'll be going through pathfinding, which I believe would be a very interesting topic for y'all. Please scan the attendance QR code if you haven't already. So yeah, let's get started. So first of all, what is pathfinding? You might have heard of this term before. Hello. So you might have heard of this term before in several games, maybe. It's okay, it's okay. Well, yeah, for those that have just joined, please scan the QR code first. And make sure that you have already pulled the most recent commit changes to the repository. I have just pushed it yesterday because I just found the time to do so. So, yeah. So back on topic. So what is pathfinding? Does anyone have any ideas? Maybe from the games that you have played before. You might have heard of this term. AI from point A to point B. Yes, okay, so it's basically just to get an AI from point A to point B. That is a very simplistic response to it, and it is correct. So basically, pathfinding is the sort of a term that is coined to let us move our AI around, and we allow them to move intelligently in ways that where it can avoid obstacle, where it will find the most optimal path to get from one point to another, and then it will also follow the geometry of the terrain or the stage and the level that you have designed, so that it won't just phase through walls and fall down through your terrain and clip through everything. It won't try to do that. Instead, it will try to follow the geometry, and then we will be able to make it look convincing to the players that the bots are actually intelligent. So, okay, before I show that slide, does anyone have any idea or want to take a guess at how we can try to achieve this? How can we? Let's cut down this a little bit shorter. How can we find the shortest path from one point to another? Anyone here has took data structures and algorithms class before or is taking one that want to share their findings? Dijkstra, yes. So Dijkstra's algorithm, one of the simplest way to find the shortest path from one point to another. So we know that it's a graph traversal problem, and we can actually model AI pathfinding to be the same. Okay, and in fact, we are usually going to model it as a graph problem as well. So we can model pathfinding as traversing a graph. For those that are currently taking a data structures and algorithms class, like 2040 or 2040S, this should be in week 8 or week 9. So you probably haven't gone through it yet. So the way how we sort of do this in the game engine itself is that we try to subdivide the terrain into small cubes or small polygons. And each cube is its own node in the graph. The nodes are connected to all the other cubes or polygons that are directly next to it so that we can form a complete graph with all the nodes on the same piece of terrain. Then we can just do graph traversal. And these are obviously the several most common graph traversal techniques that you'll be learning in the data structures and algorithms class, or you've learned, which is depth first search, breadth first search, Dijkstra's, Bellman-Ford, and Floyd-Warshall. Each has a differing complexity. So, what is the fastest one here? call your memory? Take a guess. I mean, it's probably the most famous one of all. Okay, I'm not gonna wait for an answer. It's Dijkstra. So Dijkstra is the fastest one, and as we know, games should be fast. There's this joke about Monster Hunter Wilds only being able to run for 60 frames with the latest hardware with frame generation, so it's absolutely horrible, right? And it doesn't give you a very good player experience if your games just don't run at 60 FPS at least. So, you'll probably go on forums and see that people complain that why is this game so slow? Why am I still playing it? Right. So, the basic thing in terms of satisfying players' need for any kind of game is that it should be fast. It should be performant. You should be able to play it very easily. So, the most efficient algorithm is Dijkstra, at least from the five that I have shown you. The time complexity is V plus E log V, where V is the vertex in the graph and E is the edges in the graph. So as you can see, this is not so linear. It goes slightly above linear, but it's not until quadratic time. And it actually finds the shortest path from a single source to all the nodes in the graph that it has traversed through, unless you stop it once you got to the destination. Which is actually kind of redundant because in one way or another, for games, at least for AI pathfinding, we don't actually need to know what is the shortest path to go to all destination from a single source. And then we need to update like 60 plus times per second for ideal user experience. You don't want your AI to not change its destination when it's chasing the player after 1 second, and it's just going to go off course. Right. So these are some concerns in terms of player experience. You want your AI to be able to accurately find where it should be going in the fastest time possible. So we need a faster algorithm, ideally one that does not traverse all the nodes. So this is where the computer scientist comes up with a very genius solution. And it's a modified Dijkstra solution. We call it the A-star search algorithm. So it's quite heavy in terms of algorithm. You probably don't need to know this to use the navigation though. So the A-star search algorithm has the worst case time complexity of E log V, which means it's less than linear in one way or another. And it has a space complexity of O of V, so it only needs to store all the vertices. So it finds a short path from the source to the destination. Not necessarily the shortest, but it will be a very short path that is a good enough solution to what we want to achieve. So, even when you walk around in real life, you probably won't be able to find the shortest path to go from one point to another. And we just want to get a very short path that is good enough. So this is what this algorithm is made for. There is no performance overhead because we practically won't need to we won't need to find all other destinations before getting to our destination. And it's very good for games. So right now, A-star is the most widely used pathfinding algorithms in game engines. You can find them not only in Unity, you can find them in Unreal, Godot, and any other game engines that comes with built-in pathfinding support. And even if you go and use an engine that does not have a pathfinding support and you have to install an additional package for it, it's most likely using A-star search algorithm as well. So go into how it actually works. We will have to dive into how algorithms classes are. And so recall in Dijkstra, we will assign every node with some kind of estimate of we'll assign it with some kind of like a shortest cost to get from one point to that particular node, from one node to that node. So the way how we model this is that instead of having the exact shortest so far, we will model it with an estimate. So this estimate is modeled with the exact cost plus some sort of heuristic. Normally in this case in games, we will make this heuristic to be the distance between these two nodes in the 3D space or the 2D space. So it would just be the Euclidean distance between them. And we will try to estimate the cost to go from this node to all its neighboring nodes with this relationship. Then, as we traverse through the node, we will find the one with the lowest estimate cost. Then we will compute the lowest estimate cost for each neighbor of it. Then update the lowest cost if it's not the lowest. And then we will put all of those neighboring nodes into the same queue, and then we pop it out again. It's as simple as that, and it will return a good enough path to go from the point to the destination. I mean, if you are interested in looking for the invariant, you can try to prove it. I'm not an algorithms guy, so I can't do it for you. So, all the geek talks away, okay? Apologize for that, but I want to make it a little bit longer. So, we will go into NavMesh, and NavMesh is actually the library or utility that is available directly in the Unity engine. It's currently available as a base package. It has been a downloadable package for several versions now, I believe, since Unity 2018. So it implements almost all the stuff we need for AI pathfinding. So it gives you the utility for you to transform your 3D terrain into a graph problem. It helps you subdivide the terrain into these small polygons. It does the pathfinding. It runs the A-star search algorithm for you. It moves the entity for you, so you don't actually need to implement all those movement logic that you would usually need to do. And you will be able to easily add or remove obstacles and navigable surfaces during runtime or during compile time. It's as simple as just adding the stuff and rebake the terrain. So the way how it does is when you bake a NavMesh, it subdivides the mesh surface into small polygons, and it stores all the polygons as a nodes in the graph, and then you compute it with a star search algorithm to find the shortest path to go from one point to another on this NavMesh. So let's show you guys how it's done. So with the updated package, you should be able to see this new pathfinding scene here that has this very small little playground that I set up with Unity's Pro Builder. So as you can see, we just have a very simple playground setup here. You know, you can go up and down. So how we can add a NavMesh is as simple as going to one of the terrains that you want. In this case, we have a parent object for all of the terrains, so that it's much easier for us to manage it. So I just click on this parent object, and as simple as just adding the NavMesh surface, I have done it. But it's not baked yet. So you want to just click on bake, and then you should see all of this bluey stuff grow up on this surface. So these blue gizmos that showed up is the NavMesh. It has so now you have successfully tell Unity to change all of these terrains, subdivide them into polygons, and then convert it into a graph problem to perform the search algorithm on it. As simple as that. So the places without the blue stuff, without these blue gizmos, are the places that the AI will not be able to reach. So you'll notice that somehow around my player and my enemy capsules, I also don't have it. This is because when we bake it, by default, the nav mesh surface will bake every single mesh in the world. We obviously don't want to do that. We just want to bake the terrain. So now I'm just gonna have to change this object collection here to current object hierarchy. And now once I press rebake, it will exclude baking the player and the enemy component to it object into the nav mesh. As simple as that. So now that we know that it is this simple to add the nav mesh, we convert it to a graph problem. How can we tell our AI to utilize this nav mesh? So now I'm just going to go into our enemy script. I'm just going to edit the script. Takes a while. So in this script, we need to first of all get a reference to the NavMesh agent class object in the okay. So once we have a reference to a NavMesh agent object, we will initialize it with the get component NavMesh agent. And let me just comment out all the FSM code that we have written last week so that it's easier for me to do the demo. And calling it is just as simple as doing mnavmeshagent dot move dot set destination, and then we'll be able to set the destination. In this case, let's just do a vector 3.0. So this will try to navigate to the position 000 on the terrain. And you'll see that it works practically flawlessly as soon as I attach the NavMesh agent object onto it, the component onto this enemy. So to show you guys where 000 is, I'm just going to set this to 000. In this case, it's directly inside of this cube, inside of this rectangle, this cube, this box. Okay, it's inside of this box. So I move it away, and the expected behavior is that it will try to find the shortest path to go from this point to the point closest to this cube, which is 000. So let's just press play, and we should be able to see this in action. Yeah, and it stops. Once it reaches the destination, it will stop. And if you try to move it away, and the reason is why it keeps going back is because we set this destination update. So if we were to put this in start, and we try to run this again, once it reaches this destination, okay, it actually doesn't think that it has reached the destination because the destination is inside the cube. So it's just going to the closest point to the destination. Generally speaking, once it reaches the destination, it's going to stop navigating to save cost, because if it keeps on pathfinding from the same point to the same point, it makes no sense. So there's some kind of internal optimization here that makes it stop after it reaches the destination. Okay, so now that we know how it works, we will be able to make some stuff with it, and let us just try to do this pretty simply. I have added this mnavmesh destination in the object reference here for the enemy. So I'm just going to grab this new empty game object that I've made, and then I'm just going to put this into our script. Here. So what it's going to do now is that it will try to follow this empty game object, and we're just going to change this to be empty game m nefmesh destination dot position. So now this nefmesh agent will try to follow this empty game object's position. So let's put it on top of this. Let's just try to put this on top of the cube. I don't know if I would be able to do that. Yeah, this should be good enough. So I'm putting this on top of the cube, and what you will expect is that this will move, and then it's going to climb up the stairs, and then it will reach this destination point. At least that is what we're expecting the behavior to happen. So now we're gonna press play and see if this is actually what we want, what we have expected. And yes. So as you can see, this works just as intended. One very important thing to note though is that the reason why mine works and you guys probably doesn't is because you probably... No, I think I removed it. So if you have a rigid body object, if you have the rigid body component on your nefmesh agent, you'll notice that it actually doesn't work. Let's just let it run, and we're just going to show you guys. It'll get stuck. It doesn't move up. Right. So this is not really a bug, it's sort of like a conflict in between the internal physics update tick and how the nefmesh agent actually works. I won't go into the specifics. Just know that if you want to use rigid body physics with nefmesh agent, you'll have to go on with several more modifications to the code. It doesn't work plainly, and it would be quite a pain to do that. So generally speaking, you would just remove the nefmesh agent component. Not the nefmesh agent component. You just remove the rigid body component when you're using nefmesh agent. And if you need to implement any kind of physics, you would try to do it in the code itself, like how we have did, how we implemented the character controller. So now that it moves up properly, let us make it a little bit more happy, okay? Instead of moving it to the nefmesh destination, now we're gonna move it to the player transform dot position. So now every single frame, the enemy is going to just try to chase our player. Right, it's as simple as that. So I'm just gonna press play, and you'll see that it's gonna try to chase me. You'll be able to see where it's going to just from the gizmo itself. You can see that it runs very fast, but that's okay. I just want to have an interactive way of... Stop pushing me around. Stop. Okay, stop. I need to change the speed. So you'll be able to change the parameters here. I'm just going to change the speed to 1 so that it's not as fast. It's not faster than me. So yeah, now that I can move around, I'm just gonna run up the stairs, and you can see that it's always following me. Got stuck. You can see that it's always following me. Albeit at an extremely slow rate. Right. Then as I got onto the cliff here, sort of like the edge of the box, it's gonna try to chase me. Then, if I jump down here, what will you guys think would happen? So instead of following me to jump down from the edges, it's just going to go all the way around. And that's because in the nav mesh that it has, there is no option for it to jump. As in, there's no option for it to drop from this area to this area. Even though, as you can see here, this is a nav mesh surface, this is a nav mesh surface, but there is no connection in between here. So one of the things that we can try to do to achieve this here, so that it will be able to jump down, is as I go into my level parent in this nav mesh surface component, I can click on generate link. Okay, I can click on generate link and we can bake again. So now you will see that it will try to generate this. It will try to generate all of these jumping links. So the links here are actually determined in the agent type. So if you open agent settings, you'll be able to define the parameters of your agent. So right now my agent is not really default. By default these two should be 0. And if I make these to be 0, if I bake again, you'll see that it won't try to jump down again. But if I instead change this to a bigger value like 5, if I put it to some in-between value like 1, okay, it's not generating anything, like 2, you'll see that it will jump down from here, but not from the higher ones. If I put it to 3, okay, 3 is probably still too small, 3.5, then it will jump down from the lower cliffs, but it won't jump down from the high cliff. So this is how you can set up your terrain so that it is able to jump off cliffs if it is possible for them to do so. So for now, for demonstration purpose, I'm just going to put this to 10, and then I'm just going to show you guys that it actually works. So let me just move my agent around so that now it would be on this surface here. Okay, now I press play. Now if I try to jump down, okay, if I try to jump down here, it will follow me and then it will drop from there. The animation is not the smoothest, but we sort of have to make do with that. But yeah, that is one of the ways that you can do so. And say if you have some kind of terrain like this, where you would move one of these over, and if you jump over, you would ideally want your AI to follow over as well. So in your agent settings, you'd be able to change this jump distance to something bigger. Then it will try to jump between the surfaces, and it will generate something like this. Let me just remove the drop one so that you can see how it's working. So basically, it will be able to jump from any of these points to any of these points here. As simple as that. Sometimes, right, okay, I'm just going to demonstrate that it works first. I'm just going to pull this over, and then you should be able to see that it tries to jump over, and then it will land up on this surface to find me. It's moving so slow. Yeah. As for how to make it smoother, you just need to add character animation. I'm not going to do that. So this is how you can do it. There are certain times, right, where you don't want all of these areas to be jumpable. And the way how we can try to achieve this is that instead of having Unity generate all the links for me, I will try to generate one myself. So how I'm going to do this is by adding an empty game object and then add the navMeshLink modifier. Now this will give me this very small thing over here that looks like this. So you'll be able to change like the values of this. For example, if I try to push this to the max, and then for my width I push this over more so that this covers all of this surface over here. Now I'll change this area type to jump. Okay. And what this does is that this will create a navigable link in between these two navmesh surfaces. So now as I bake again, nothing happens. Give me a moment. Do we need it to be a bit larger? I believe it still jumps over. Let me just try this out, because I've never tried this before as well. Ah, okay. I did it wrong. Sorry. This should be rotated 90. The width should be like this. This one should be here to here. Yeah, the orientation matters. If this is a valid link, you will see it being like a little bit more grayish, more translucent instead of fully transparent. So now if I bake it again, I believe this should now work, unless I'm being stupid. Yes. As you can see, it jumped over, and with this one being so wide, it will be able to jump over from any given point that this navmesh is connected. So say you don't want it to be able to do that. You just want it to have a very small area that this will be able to jump over. In certain games, maybe you have terrains that want to encourage this behavior. You just need to make this link smaller. In this case, we just change the width like this. And then, now, as I move my enemy object over here, somewhere here. Right. As I move it over, just now we saw that it will be able to jump from here, right? Now, what you would notice that it will go all the way over here and then jump over from this area. So it is also possible for you to make this to be a walkable area instead of a jumpable area. Where is it? Here. Then it will walk over and the cost would be different. Usually jumping has a higher cost because, you know, jumping is more expensive. It consumes more data. It consumes more energy in real life, so we put jump to be of higher cost. So you won't try to jump over usually, but you'll be able to do that. So in certain games, you will probably also want to have some kind of behavior. For example, you have like a river, a shallow water that you want your agents to not cross it that often and try to find the closest bridge, for example. So the way how we can achieve this is inside of our navigation. inside of a nav mesh surface, you will see that there is this thing called a default area, where we can define our own areas here and its overhead cost. So if we define, say, the water area here with a much higher cost like 5, then it will try less to go over the water and will try to find a shorter path around the water, unless the shortest path is through the water, even with this additional cost. Now, there are some games that this would be necessary. For example, in like PUBG, your AI don't want to go through the water that often, because there is a disadvantage of doing gunfights in the water. You swim slower, your bullets sometimes misses, and you also have things like stamina. So you want to mimic this behavior where normal human will also try to avoid the disadvantage of being in water. So you'll be able to do that. And now you'll be wondering, like, how will I be able to change the surface of these things, right? So the way how we do this is that now, if I select one of my thing, right? If I select one of my thing, okay, and I give this the nav mesh modifier component. Okay, if I give this the nav mesh modifier component, I can click on override area and then change the area type to a different one. Then this will now be done in a completely different way. So this will be baked as the water surface with the higher cost for the heuristic. So let me bake again. I don't think it would, yeah, so it will give you a different color. Notice how the colors actually correspond to the things here, to give you a visual cue of what type of surface it is. Okay, so to show you guys that this actually works, I'm just going to create a very small scenario here where we will clone one of these cubes, and then I'm going to change the scale. Okay, this is not going to be like very good, but I think it suffices. So I'll have one cube here. Let's make the Z smaller. So that is like 1. So I have one cube here. I create a second one over here. Okay, I think this needs to be a bit taller. Okay, something like this would do. Something like this would do. Yeah, okay, it's okay. So, yeah, so, in some kind of scenario like this, actually let me add some rotation so that it's more like intuitive what's happening. If I do this, okay, so if I move this over here, and let me just remove this modifier, let me give this one the shorter path by distance, the modifier of water, and then we try to give this a huge modifier, for example like 20. Okay, it is very expensive, right? So generally, if we look at it normally, you would think that this AI would go here and then go here and then to find you. But because we give it so high of a cost, okay, now we bake. sorry, it's not wide enough. Okay, now I think this would be wide enough. Okay, now this is wide enough, so now it can pass. So, but instead, because the cost of going through this link is so high, it will try to find the next shortest path, which is here. So yeah, there are times where this behavior will be useful. So you just need to find a reason to use these kinds of powerful tools at your disposal. So this is how you can change cost, and you can also modify the things on your AI in your navigation type. I'm not gonna go through how what all of these means. You can try to experiment it around. So did I miss something? No, I don't think so. So the final thing on the list is this on your agent. Where is my agent? So on your NavMesh agent, there's actually this thing called obstacle avoidance. So the way what this does is that it will try to avoid certain obstacles, but it will not, like, it will sometimes still bump into it, but it will try to avoid it, and that obstacle might not be part of the NavMesh. Let me show you what I mean. So, for example, now, if I create a cube, okay, I put the cube here. Okay, I put the cube here. Now, if I bake now, you'll notice that the cube is not being carved out. There's no area around it, right? This means that this cube is right in the middle of our navigation. So if I have this player right over here, what's going to happen? It's just going to bump into the cube. And it's just going to phase through it. So there are times where you would want to avoid putting these kinds of obstacles in your NavMesh. For example, it's a runtime generated obstacle. In games like Call of Duty, you can put like sandbags around the area. These are the things you want to avoid. Like, for example, if you drive a car around, your AI would want to avoid your car when pathfinding. But you don't want to carve it. If you make the car to be part of the NavMesh, and then every time it moves, you have to bake the NavMesh again, so that the NavMesh has an empty area around the car. You could imagine that if you bake a NavMesh every single time, every single frame, it's going to cost a lot of performance cost. So generally speaking, for runtime only objects, we will try to just give it the obstacle tag, so that we don't need to rebake the NavMesh, and the AI will try to go around it. Let me show you how it's done. It's as simple as going to the thing, and then we add a NavMesh obstacle component to it. Okay. Now this is going to show up with all of these. It tells you like the size, the center, the shape of it. Generally, there's only two shapes because for simplicity's sake, it's much easier to do calculations like this. So there are two modes to this. You can either turn on carve or you turn off carve. If you turn on carve, it's essentially doing the same thing as putting this in the NavMesh. Every time this object moves, you have to rebake the NavMesh. This is exactly the behavior that we don't want to happen. So we're just going to turn off carve here, and we're just going to rely on this AI's obstacle avoidance to do it. I have never done this before, so I don't know if this is going to work. See? So as it gets close to the obstacle, it tries to avoid it, and it goes through the side instead of phasing through it as the first time we did. So it will still try to find the closest path, but as soon as it reaches an obstacle, it will try to avoid it. And if you give this a slower value, as you can see, the quality here is there. If you make it none, it's just going to ignore all obstacle and just phase through it again. It's as simple as that. Not the behavior we want. Correct. And now we have this collider. If I add like a rigid body onto this, we should be able to see this. I don't remember this NavMesh override physics. It does. So it sucks, right? So yeah, there are times where you just don't want this to happen, and since the NavMesh agent doesn't allow you to put rigid body on it because of conflicting stuff. If you have these kinds of things in your terrain, instead of having collision detection, it will have a big NavMesh or obstacle. That's it. Unless you want to go into writing your own code to try to avoid these kinds of conflicts, which in theory will be quite troublesome, so we don't usually do that. So there are these kinds of other things that you can add into your NavMesh agent. You can try to look at it whenever you have time. So as simple as that, I believe this should be all the components that I need to look at, and yes. Questions? No questions. So several things that I would like to say in terms of tips and tricks to using NavMesh is, again, avoid baking NavMesh on runtime unless it is necessary. So the reason why I say this is because every single time you bake a NavMesh, it has to go through the entire terrain again and then try to subdivide it into polygons and transform it into a graph ball. If your map is small, it should be still okay. But if your map is bigger, your terrains are more complicated, you have a lot of different elevations and heights and everything, then this will not be a very feasible way of doing it. So instead, you should try to use the NavMesh obstacle, as I have demonstrated just now, to let the AI avoid runtime spawned objects. And you should also avoid setting a new destination every frame. Because every single time you set a destination, it needs to pathfind to it again. Now, if you set a new destination to the same location, generally speaking, I believe there is some form of optimization behind the scenes that Unity does with this package so that it doesn't recalculate. But still try to avoid this. Instead of setting it every frame, you can probably try to set it on an every fixed interval of like 0.1 second, 0.2 second, do it in the coroutine so that it's much easier for you to do it. So that is actually all from my slides. And we have a lot of time left today. So for this time, you can try to integrate NavMesh into the finite state machine that you have designed last week. And try to get it working. Okay, questions? Questions? Sorry? You guys know him. Okay, questions?
How do they do the avoidance?
The avoidance,
It's just force, like just trying.
I believe, okay, I don't have first-hand knowledge on this because I don't really research this. I believe how they do it is that as soon as it reaches an obstacle, it will map that path where this obstacle is to be of very high cost, and then it tries to avoid it. But I don't know if this is actually the way they do it. But that could be a very intuitive way of doing so. Questions? Other questions? No questions? No questions? Good. So if there are no any questions, you can use this free time to work on. I'll be around here to help you out if you have any technical problems with using the NavMesh. And yeah, I guess I'll see you guys next week. So a sneak peek into what we'll be doing next week. As mentioned last week, next week we'll be going through behavior tree, and we will use the package that Unity has provided us for visual scripting of behavior trees. That would give a lot of freedom for you to work with, and you don't actually need to write a single line of code, which is awesome. Okay. Yeah, so I'll see you guys next week, and thanks for coming.